Hello. This video is for the Organic Chemistry Lab number 2, and we are talking about polarimetry. So why does this phenomenon occur? The phenomenon that we are talking about is polarimetry, or the study of how molecules bend light. This happens because these compounds are made of molecules with chiral centers. These molecules interact with plane polarized light and lead to a change in where the polarization of the light happens. Chiral center is a carbon that is bonded to 4 different groups. So an example of that would be something like this molecule here. We have 2 chiral centers within this molecule. We have this carbon here, which could be classified as something like carbon 2. So this would be 1, and this would be carbon 2. And this carbon has a methyl group, is attached to an OH group, and a CH3 group, as well as another carbon group. So this carbon itself is a chiral center. Carbon number 3 is also a chiral center in this molecule. We have a methyl group, a CH3 group, a different molecule, and another carbon group. So these are the chiral centers that we're talking about that are rotating and changing the way that the light is polarized and the way that the light goes through the polarization filters. Observed in this lab, why do the various compounds alter the results? What causes the differences? The differences seen in this lab are the different functional groups, the number and size of the chiral center. All 3 compounds have chiral centers. Fructose is a ketone group as its functional group. And they have a lot of large centers with strong left rotation. So all of these centers for the fructose are large, have a lot coming off of them, have large molecules coming off of them, and have a great left rotation. So they spin quickly and they spin to the left, which is why we have a large negative number in observed and specific rotation for them. Glucose is an aldehyde group which has a lot of large centers and a strong right rotation. So it's almost the exact opposite of fructose in the fact that it rotates to the right instead of to the left. And this is why we have a large negative number in observed and specific rotation. I'm sorry, a large positive number for observed and specific rotation. The L-aniline is an amino acid which has 1 small center and a weak left rotation. So this one has a small center and would look more like this if these two were not the same, because a chiral center has to have 4 different molecules. But then it has a weak rotation, a weak left rotation. So it's rotating less and it's catching the light less, so it's moving the light less. And this gives a small number for the observed and specific rotation. How do we know that these molecules are all optically active? We know this because they all have at least 1 chiral center, which means that at least 1 center is spinning and rotating, catching the light and changing it. As observed in the experiment, the extinction point changes with the compound when the compound is put over light in the polarized sheets, proving that they are optically active. So because that extinction point changes, it shows that the molecules are catching light and changing the way that they are reflecting. How does the concentration, purity, and identity of the substance affect the results? The higher the concentration, the more chiral molecules, the more rotating centers to change the light. So if I have just 1 molecule rotating, it's only going to be able to catch the light that it interacts with. If I have a lot of molecules rotating around, they're going to be able to catch more light, and that's going to be able to change that polarization point more. The purity of the compound has to do with the impurities in the mixture. If there are a lot of impurities, it will interrupt the changing of the light and block some of it naturally. So we have some substances and compounds, when mixed together, have very little impurities, and you can see that they're basically clear. And light passes through this very easily. Then you have some compounds that have a lot of impurities in them, and you can see that when they're moving around. These impurities will block light and will change your experiment if they're allowed to be within your floating. So for this experiment, we had to wait and make sure that all of these particles settled, and then made sure to use just the liquid and keep all of these solids that are starting to settle in the bottom here within this centrifuge. That way, we can look through and let the light pass through this space here that is much clearer. The identity of the compound lends to the specific rotation. Each compound will be different, and the speed and type of rotation will change how the compound interacts with light. Like we were talking about a chiral center rotating left or right, and the size of that molecule, so the amount that it'll catch the light of. What has to occur for this phenomenon to be observed? To be able to see this happening, you must have a compound that is optically active, meaning that they must have these chiral centers that are going to move. The light must be able to pass through it, so it needs to be clear. You need to be able to have the light passing through it. So it either needs to be in a solution so that it can be clear, even if it has impurities, or it needs to be something transparent. So you can't test the optics of a napkin or the polarimetry of a napkin because light cannot pass through it. There also needs to be enough of the concentration. There needs to be enough, or the concentration must be high enough to see the rotation. So if I put a very small amount of liquid in a large jar, so this was the setup that we were using for this lab. This was my light. If I put only a small amount of liquid into the jar and then start rotating my polarizing sheet on top as well, then you're not going to be able to see the light passing through it. It's not going to change it that much because there aren't enough molecules to do that changing. So also, if it's extremely diluted and those molecules are very spread out, you won't see as much of that polarimetry that you're trying to see within this. Thank you.